Hello friends, welcome to engineering tutorial. Now in my previous few videos I discussed about the concept of single sideband suppressed carrier amplitude modulated signal, the various methods of generation of SSPSC signal, and also the process of demodulation of an SSP amplitude modulated signal. Now in today's video we will touch the concept of frequency modulation. We discussed about the basic concept of frequency modulation, the generation of a frequency modulated signal, the waveforms, the modulation index, the frequency deviation, sidebands, and other related concepts. Now in today's video we will be discussing about the methods of generation of a frequency modulated signal. So please check out my videos related to frequency modulation in my channel Engineering Tutorial before going into this video so that you can understand it in a better way. So let us start the generation of a frequency modulated signal part. Now as you can see here, there are mainly two methods which are used for the generation of a frequency modulated signal waveform. The first one is the Armstrong method, which is the indirect method of generation of a frequency modulated signal, and the second one is the parameter variation method, which is the direct method. Okay, so we have two methods of generation of a FM signal. First, the Armstrong method. Second, the parameter variation method. Now we'll be discussing each of these methods separately in detail. In this video, we will be discussing about the Armstrong method of generation of frequency modulated signal. And in a separate video, we will be discussing about parameter variation method. So let us start the Armstrong method of generation of a frequency modulated signal. Now, this is the block diagram of the Armstrong method of generation of a frequency modulated signal. Okay, so this is the indirect method of generation of a frequency modulated signal, and the type of frequency modulated signal which we get is the wideband FM. Okay, so wideband FM, as we know, has greater number of sidebands, and also the modulation index, bandwidth, and frequency deviation is more in case of wideband frequency modulation as compared to narrowband frequency modulation. So in Armstrong method we will be getting a wideband frequency modulated signal. So this is the block diagram of the Armstrong method of generation of FM signal. So the components which are involved are, first of course we need a message signal which contains the actual data and information to be transmitted, and we need the carrier signal EC cos omega CT, and the message signal is EM cos omega MT as usual. Here the carrier signal is generated from a crystal oscillator, and apart from these two we have an integrator, a narrowband phase modulator, and a frequency multiplier. Okay, so don't be confused about this narrowband phase modulator part. We'll be discussing about it in the description part. So please draw this diagram in rough or get a screenshot of it so that you can understand the upcoming steps in a better way. Okay, so draw this diagram roughly or get a screenshot of it. Now, this is the working principle of the Armstrong method. So first the message signal input is passed through the integrator. Okay, the message signal is given by Em cos omega mt. Mt is equal to Em cos omega mt. The output of the integrator is of course the integration of the above signal, which is integration of mt dt. So of course we will get Em by omega m sin omega mt, but here we have not mentioned that. Of course it will be integration of cos will be sine, and this omega m constant part will go to the denominator, so we will get Em by omega m sin omega mt. Now the output of the integrator is fed as input to the narrow band phase modulator. Okay, the output of the integrator is fed to the narrow band phase modulator. Now the function of the phase modulator is to phase modulate the carrier signal which is generated by the crystal oscillator with respect to the integration of the message signal. Okay, not the message signal but the integration of the message signal. Okay, so here the integration of the message signal acts as the baseband or modulating signal waveform to perform phase modulation. So please, it is the critical part here. The message signal mt does not perform phase modulation, but the integration of the message signal, which is the output of the integrator, which is fed to the narrowband phase modulator. The carrier signal is phase modulated with respect to the integration of the message signal, not the message signal mt, but integration of mt dt. Okay, so this part acts as the message signal for phase modulation of the carrier signal from the crystal oscillator. Now we have discussed about phase modulation in my video related to phase modulation basic concepts. So of course the output of a phase modulator or the mathematical expression for phase modulation is given by Ec cos omega Ct plus Kp into integration of mt dt. Here Kp is the constant of proportionality or the phase modulation constant. Note here that normally the phase modulated output, normally if we have a carrier signal Ec cos omega Ct and a message signal mt Em cos omega mt, we would have got our output as Ec cos omega Ct plus Kp mt in normal case when the message signal would have been empty for phase modulation. But here, as I said, the message signal is actually for phase modulation, the message signal is integration of mt dt, which is the output of the integrator which is given to the phase modulator. So this signal integration of mt dt acts as the modulating signal. So we get the narrow band phase modulated output as Ec cos omega Ct plus Kp integration of mt dt. Okay. Now it can be further simplified as Ec cos omega Ct plus Kp Em cos omega mt dt. So we have replaced or substituted mt with Em cos omega mt, and then we have performed integration over it. So we get Kp Em by omega m sin omega mt. Now this is a frequency modulated signal waveform. So if you have seen my video related to frequency modulation, you will understand that this part Kp Em by omega m is actually the modulation index beta. Okay, Kp Em by omega m. So we get the narrow band phase modulated output as Ec cos omega Ct plus beta sin omega mt. This is a narrow band frequency modulated signal. Okay, this is a narrow band frequency modulated signal. It is because the modulation index beta value is less, the frequency deviation value is less, and also it has lesser number of sidebands. So what we need to do is to convert this narrow band frequency modulated output into a wide band frequency modulated output. Now Now we achieve this with the help of a frequency multiplier. This signal is fed to the frequency multiplier. So please refer to the block diagram which you have drawn roughly and or have taken a screenshot, so that you understand these steps in a better way. Now, the output signal of the narrowband phase modulator is very low modulation index, as I have said. The beta value is very low. So, in order to get a wideband frequency modulated signal by increasing the value of beta, we need to use a frequency multiplier. Okay, we need to use a frequency multiplier. So, what the frequency multiplier actually does is that it increases the carrier frequency multiple number times, n times, let's say. Okay, it increases the carrier frequency n times. So, we get an instantaneous frequency value as n omega c plus n kf mt. In normal circumstances, it would have been omega c plus kf mt only, but here the factor n gets multiplied with both of them. Okay, n omega c plus n kf mt. So now the frequency deviation is given by delta omega, which is the maximum difference between the instantaneous frequency and the carrier frequency, or the maximum departure of the instantaneous frequency from the carrier frequency, is given by delta omega by n omega c plus n kf mt minus n omega c. So n omega c gets cancelled out. We get the frequency deviation as n kf em. Mt is em cos omega mt. Okay. Now the maximum value of cos is 1, so we get the maximum value of frequency deviation as n kf em. Now the modulation index value is actually the ratio between the frequency deviation delta omega and the modulating signal frequency. So we substitute the values. N kf em by omega m which is equal to n into kf em by omega m. Mark that kf em by omega m is the old modulation index. Okay, kf em by omega m is the old modulation index, the normal modulation index. So the factor n gets multiplied with the modulation index, old modulation index. So the new modulation index is n times the old modulation index. Okay, so by this way we get a wideband frequency modulated signal. Okay, now suppose we choose the n value as 2. Okay, so the new carrier frequency will become twice of the old carrier frequency. The new frequency deviation will become twice of the old frequency deviation, and the new modulation index will become twice of the old modulation index. If we choose n as 3, the new carrier frequency will become 3 times of the old carrier frequency. The new frequency deviation delta omega will become thrice of the old frequency deviation, and the new modulation index beta will become thrice of the old modulation index. Okay, as modulation index is directly proportional to frequency deviation. So we get the final frequency modulated signal output or wideband frequency modulated signal output as EC cos n omega ct plus n kf integration of mt dt, or EC cos n omega ct plus n beta sin omega mt. Note here that the factor n gets multiplied with each of the terms, the carrier frequency part and also the integration of the message signal part. In both the parts we have we see this n term, the n constant being multiplied. So this is the wideband frequency modulated signal output, which is the output of the frequency multiplier. So in this way, by using the Armstrong method, we generate a wideband frequency modulated signal with high value of modulation index, frequency deviation and high carrier frequency, and also the number of sidebands in such a frequency modulated signal waveform is high. So in my next video I will be discussing about the parameter variation method of generation of a frequency modulated signal. So I hope you like this video. Please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics communication and instrumentation engineering. Have a great day. Thank you very much.